All right, let's talk about something that sits at the very heart of physics. Today, we're diving into a really cool theory that flips our whole understanding of particle mass on its head. It asks a simple but huge question. What if the mass of a particle isn't some random lottery number, but is actually cooked up from a hidden recipe?
I mean, really think about it. You've got the electron, which is incredibly light, and then you have the top quark, which is just monstrously heavy. All these fundamental particles have these very specific masses, but the numbers look like they were pulled out of a hat. There's no obvious pattern, no rhyme or reason. It's a huge puzzle. So what if there is a pattern, but it's hidden inside the particles themselves?
So here's how we're going to break it all down. First, we'll look at the mystery itself. Then we'll get into this awesome idea of particles as recipes. The real core of this explainer is going to be section 3, how we figure out the starting mass of our ingredients. After that, we'll see how those ingredients get cooked, and we'll wrap up with a final thought that might just change how you see reality.
Okay, so let's start with what the mainstream view, the standard model of particle physics, tells us. Now, this model is unbelievably successful, but it's got this one kind of nagging blind spot.
You see, the standard model doesn't actually explain why a particle has the mass it does. Physicists have to measure the mass in an experiment and then just plug that number into the equations. It's treated as a given, a fundamental constant. But the theory we're exploring today says, hold on a second. What if mass isn't fundamental at all? What if it's an emergent property, something that comes from what a particle is made of?
And to really get our heads around this, we're going to use a fantastic metaphor. We're going to think like chefs. So for the rest of this explainer, I want you to stop thinking of particles as these tiny, indivisible dots. Instead, picture them as complex dishes, made from just a few core ingredients, all following a very precise recipe.
Every great recipe needs a base, right? You need your flour for a cake or your stock for a soup. In this model, that's the generic particle. Think of these as the plain, unflavored, foundational versions of quarks and leptons. They have a starting mass all their own, and we're going to see exactly how that's calculated in just a minute.
But a base ingredient is just the start. You need to add flavor. That's where scalar bosons come in. These are the spices, the sauces, the secret ingredients in our cosmic kitchen. They interact with the generic particles and, bam, they can radically change the final mass, making it way bigger or way smaller. They are the agents of transformation here.
But wait, it gets even deeper. What determines the weight of our flour to begin with? Well, this model proposes that even our generic particles aren't fundamental. They're built from even smaller things called reshans. It's like finding out your flour is made of specific types of grains. And it's the precise combination of these reshans that sets the starting mass of the whole recipe. This is the bedrock of the whole idea.
And this right here is the heart of it all. This is the part I really want you to see. If mass comes from a recipe, then how do you weigh the ingredients before you start cooking? Well, it all boils down to the specific way those reshans are arranged inside the particle.
The method is actually pretty straightforward. You look at the particle's internal structure, specifically for things this theory calls T-expressions, and all you have to do is see how they're grouped. If a T-expression is all by itself, unpaired, it gives you a mass factor of 10. But if it's paired up, that pair only gives you a factor of 1. You just multiply those factors together, and then by a base number of 20, and that gives you the particle's starting mass in something called electron units. Simple as that.
So, let's see how this works with a real-world example. A generic D quark, because of its Rishan structure, has just one of those singular T expressions, so it gets one factor of 10. That gives it a starting mass of 200 electron units. But now look at the generic U quark. Its structure has 2 singular expressions, so you get a factor of 10 from the first one and another factor of 10 from the second. The result? An initial mass of 2,000 electron units. It's 10 times heavier, purely because of its internal wiring.
Okay, so we've got our base ingredients and we know their starting weights. Now it's time to actually cook. This is where those scalar bosons, our spices, come in and completely transform the final dish.
So how does the universe decide what happens? It all comes down to a property called the combinatorial value, or CV for short. Both our generic particle and the scalar boson have one of these values. And the real magic happens when you multiply the two CVs together.
The rules are incredibly elegant. If the product of the two CVs is a positive number, the particle's mass gets multiplied by a massive factor, say 200. it becomes hugely heavy. But, and this is the amazing part, if that product is a negative number, its mass gets divided by that exact same factor. It becomes incredibly light. Just a simple plus or minus sign determines a particle's entire destiny.
Now this is fascinating. Check this out. Both the top quark and the much lighter strange quark, they start with the exact same base ingredient, a generic D quark. So what's the difference? It's just the boson you add. The only difference in their entire recipe is which scalar boson gets sprinkled in. One tiny tweak to the recipe, and you get two completely different particles. That's wild.
Okay, so here's the play-by-play. Step 1, we start with our generic D quark, which has a base mass of 200. Simple enough. Step 2, we add a scalar boson plus. Now this one is special. It actually transforms the D quark. It converts it into a generic U quark, and remember, that one has a much higher base mass of 2000. So now the rules kick in. Their combined combinatorial value comes out positive, so we have to apply that huge mass factor of 200. You see where this is going? And boom, there it is. 2000 times 200, that gives us a final mass of 400,000 electron units. Just by following a clear set of instructions, we've gone from a pretty simple base particle to an absolute heavyweight. The system works.
Now let's see the exact same rules work in the complete opposite direction to create the electron. The model shows that the generic electron starts with a mass of 200 electron units. But this time, it interacts with a different boson, and their CV product is negative. So what does the rule say? We divide. 200 divided by 200 gives us exactly 1 electron unit. The same system, the same rules, just a different sign, and you go from the heaviest particle to one of the lightest.
We're going to try to build a heavy particle, the bottom quark, and see how these simple ingredients can cook up a really large mass. The recipe for a bottom quark in this framework is actually pretty straightforward. You just need one generic D quark, that's our base, and then you add 2 identical spices, 2 particles called boson zeros. And the model gives us a nice little visualization of this. You can see it right here. The generic D quark on the left combines with 2 of the same boson zeros. It's this very specific 3-part combo that defines what we're about to make. So let's do the math. How does this work? We start with our generic D quark, that's 200U. Then the 2 boson zeros interact with each other in a way that, according to the rules of this model, spits out a mass factor of 40. In this case, the interaction is positive, so we multiply. 200 times 40, and you get 8,000 electron units. And there you have it. We've just built a heavy bottom quark from a few simple pieces. Okay, so this model can build things up. It can make heavy particles, but can it make really light ones? This is where, for me, it gets really elegant. Using the very same toolkit, we can actually go in the other direction and slash the mass. Let's try to build an up quark. Now, the recipe for an up quark starts with that same base ingredient, our one generic D quark. But this time, we're changing up the spices. We're going to add 1 boson zero and 1 boson plus. And here's the picture of our new recipe. The D quark is still there. It's still our base. But look, the interaction is now with 2 different bosons, 1 boson zero and 1 boson plus. That new ingredient, that's the key. That's what changes everything. And this is where the magic happens. We're starting with the same 200U base mass. Now, this new combination of bosons, the 0 and the plus, also happens to generate a mass factor of 40. But, and this is the crucial part, according to the rules, this specific combination triggers a division instead of a multiplication. So, we take our 200, we divide by 40, and we get just 5 electron units. A really tiny mass from the exact same starting parts. So let's just put that side by side, because this is the whole point. With the exact same starting mass of 200U and the exact same resulting mass factor of 40, we've just created 2 completely different particles. For the bottom quark, we multiplied, and we got a heavy 8,000U. For the up quark, we divided and got a light 5U. The entire result is just determined by the recipe of bosons you happen to use. Now, this is where the model goes from being just an interesting idea to something that really makes you stop and think. Because as the creators applied this recipe across the entire lepton family, the electron, muon, tau, and all their neutrino partners, they apparently stumbled onto a pattern. A stunningly consistent hidden number. And that number is 160,000. Now, the model claims this is not a coincidence. It's a consistent mass scaling factor. The claim is this: if you take the mass of a charged lepton from any generation and you divide it by 160,000, you will get the precise mass of its neutrino partner. Let's put this rule to the test with an example. Take the tau lepton. This model calculates its mass at about 4,000 electron units. Okay, now do the math yourself. What's 4,000 divided by that magic number, 160,000? It is exactly 0.025 EU, which is the model's calculated mass for the tau neutrino. And according to the authors, this relationship just clicks into place for each and every generation. So where in the world does a number like 160,000 even come from? Well, this is where the authors make a really striking connection. They state that this value is comparable to the mass of the W boson, the very particle that carries the weak nuclear force. The implication here is huge. This model's scaling factor might be directly linked to one of the fundamental forces of nature. And believe it or not, it gets even more intriguing. The model suggests that the 3 generations of particles we know about aren't just some random groupings. They might be tied directly to that combinatorial value we talked about earlier, revealing a kind of hidden symmetry in the universe. Just focus on the bottom row of this table, the first generation. These are the particles that make up you, me, and everything we can see around us. According to this model, both the quarks and the leptons in this fundamental generation share the exact same combinatorial value of -1. It suggests a deep connection where we've only ever seen separation before. So let's just quickly recap the core claims of this model we've just walked through. First, the big one. Mass isn't fundamental, it's built. Second, a few really simple rules can produce the huge range of masses we observe in the universe. Third, there's that consistent scaling factor of around 160,000 that seems to connect leptons to their neutrinos. And finally, the authors claim their results are consistent with the measured values we already have from the standard model. And all of this leaves us with a final, really fascinating thought. This model treats mass not as a given fact of the universe, but as the end result of a calculation. It reframes a constant of nature as something that emerges from a deeper, simpler system. So it really makes you wonder, if the mass of everything is just the outcome of a cosmic recipe, what other parts of our reality are just waiting for us to figure out their instructions?